Thank you all for coming to all these lectures this whole week. It's been a very wonderful opportunity for me. And if some of you would like to continue doing research in this area, I would be glad to discuss open questions with you either later this afternoon or by email in the future. Feel free to contact me. Today will be a very geometric talk. I'm hoping to give geometric explanations both of Strawson's algorithm for 2x2 matrix multiplication and for this Bini, Capovani, Lotti, Romani border rank algorithm. Both of these were presented in the very first lecture in coordinates. They looked rather ad hoc. I would like to convince you that both of these are very geometrical and have beautiful geometry associated to them. I will review the last few things I said at the end of the last lecture. I went a little quickly. So if we look at the points, so now I'm going to work in the general setting of secant varieties of an arbitrary subvariety of projective space X. And inside the secant variety are the points on an honest secant R-plane. And if one wants to study the decomposition of such points, for example, it's a large topic of research that I haven't touched upon, is when is the decomposition of a point essentially unique up to trivialities. This is a big area of research. It's very important for applications to engineering in other areas. So in order to make that study of decompositions, one forms this incidence correspondence, which is essentially the variety of decompositions. The fiber over a point in this variety is the set of decomposition of rank R decompositions of this point. Now, we in this lecture series are interested in variety with symmetry, namely the Segre variety, and we also are interested in a point with symmetry, the matrix multiplication tensor. So we introduce these two groups, the group preserving our variety X and the group preserving the point we want to decompose, which is a subgroup of the variety preserving X. Now, if we have a particular expression of our point V, this group will act on that expression and then generally move it around. And the moral of that statement is we should not study individual expressions. We should study their orbits. That, for us as geometers, is much nicer. It's a lot easier to study the geometry of an algebraic variety than a geometry of a point, because all points kind of look the same. But varieties do not. They look different. And so what we should study is these orbits, or even eventually these orbit closures, and these will give us much more information about our original point that we wanted to study, in our case matrix multiplication, but one should interpret it more generally than just a particular algorithm. Now, I also would like to remind you of this generalized Kamon conjecture, that when your variety is the Segre variety of the same projective space, so D copies of some PA minus 1, then first of all we have this symmetry group I didn't mention explicitly so much. We have a single change of basis in our vector space, and we have the permutation group acting on the factors. And Kamon originally conjectured this just for symmetric tensors, but we generalize it to arbitrary tensors with some discrete symmetry. If a tensor has some discrete symmetry, then there should be a decomposition of it that also has that discrete symmetry. One more thing, matrix multiplication is gamma equals Z3 invariant. It has this cyclic symmetry because of the trace. Well, let me just remind you, trace of x, y, z is equal to the trace of y, z, x, etc.
Is there any reason the Kamon conjecture stated is only for discrete?
Well, what we're going to discuss is usually the continuous group will not fix an algorithm. It will move it to another algorithm. That's just based on experience. See, the role of these two groups is very different. This is just change of basis. So this is really just relabeling our algorithm. Whereas this thing really, it is not. It's changing something more dramatically. So that's a very good question, though. Right. So where was I? Yes. So we have this, this GMN is this, well, in this case, let me write it as GLN 3 copies cross this Z3. So this is, before I would write this as GLU cross GLV cross GLW. And I should really be writing PGLU, PGLV, and PGLW. And later on, for convenience, I'll write SLU and SLV and SLW, because that's the effective action. And so we should look for algorithms invariant under cyclic permutations. So any questions? Okay. So U, V, and W will be C2 now. And I'm going to talk about Strawson's algorithm.
So your notation GT is the group fixing this given tensor P?
That's correct. Just like here. So, so we have this sitting inside A tensor B tensor C, which is C4 tensor C4 tensor C4, remember. And to talk about Z3 invariance, oh, and I should write this as identity on U, tensor identity on V, tensor identity on W, where this is U star tensor V, linear maps from U to V. This is linear maps from V to W. And this is linear maps from W to U. To talk about Z3 invariance, we need to identify A with B with C. And to do this, it's sufficient to identify U with V with W, because if this is linear maps from U to V, and I identify U and V, this becomes linear maps from U to U, and this will also be linear maps from U to U, and this will also be linear maps from U to U. That'll give me the identity. So if I identify my small spaces, I get for free an identification of the larger spaces. So choose some linear isomorphism, let's call it A0, a linear map, a linear isomorphism from C2 to C2, and then another one, B0, a linear map from V to W, and then this gives us C0, which will be A0 inverse, B0 inverse from W to U. And if we work in bases, we'll just set these to be the identity. The identity matrix. And those choices have used up 2 out of our 3 copies of SL2. Now, our third copy of SL2, our third freedom, is really embedded diagonally, but I'm going to sort of break symmetry and think of it as SLU. So for convenience, think of third copy as SL2 is SLU. And so our hope is to get this orbit's worth of algorithms. So we should have, in our case, some SL2 3 copies worth of algorithms. So SL2 is 3-dimensional, so we want 9-parameter family of algorithms in our case. That's our orbit. Is perhaps it may be a little smaller than 9-dimensional, but it's up to 9-dimensional orbit. And we have already, our choices already have already fixed 6 of those 9 dimensions, and we have 3 dimensions left of freedom. And if you believe that we have all possible algorithms, then somehow, once we use up all 3 copies of SL2 geometrically, the algorithm should just be sitting there in front of us, because we want to get the algorithm purely from geometry. So recall that SL2 acts 3 transitively on CP1, which is the 2-sphere, i.e. can send any 3 distinct points to, say, 1, 0, and infinity. Or 0, 1, and infinity, I guess. So, and that completely uses up SL2. So choice of U1, U2, and U3 in PU should give a unique algorithm. Yeah, plus this choice of A0 and a B0 that we already made. Okay. Now, unfortunately today we do not have a lot of time together. I'm just giving only one lecture today. So I will skip the proof of the following theorem, but I will tell you how to prove it if you're motivated. Let me just introduce some notation. If I have some, I'll write X tensor Y tensor Z, Z3 to just be the cyclic sum. And here's the theorem. So this is Chiantini, Eichenmeyer, myself, and Ottaviani. The following is a 9-parameter family parametrized by SLU cross SLV cross SLW of rank 7 expressions for M2. So first we take those 3 points. And now, oh, I forgot to say, this U1, U2, and U3, notice that U1, U2, and U3 determine some V1, V2, and V3, because this is just A0 of U1, etc., and also some W1, W2, and W3. So these are in PV, these are in PW. But also, you know, a point in P1 determines a unique hyperplane in the dual P1, but a hyperplane in P1 is a point. So it also determines points U1 perp, U2 perp, U3 perp in PU dual. And similarly, we have points in PV dual and PW dual. So we have a collection of 18 points. And I claim if we insist on Z3 invariance and a rank 7 decomposition, there's essentially a unique algorithm. Because, see, this point will be Z3 invariant if we choose bases properly. Because these 3 matrices are the same matrix. Now, our next term, well, we'll start out. Let's start out with, we might as well. So now we need something in U star, right? Because this is in U star tensor V, tensor V star tensor W, tensor W star tensor U. So we need a point of U star. Well, we have 3 to choose from. Let's start with the first one. So U1 perp. And now we need a point in V. Well, we don't want to take V1 because U1 perp will annihilate V1 because of our identifications. So we could take V2. And then we want to use up these other points. So let's use V2 perp, tensor W1, tensor W3 perp, tensor U2. And we want this to be Z3 invariant, so let's just take its cyclic sum. Now, the choice of this could have been 2 or 3, and this one could have been 2 or 3. The rest is sort of fixed once you determine that. So we have another possibility, U1 perp, tensor V2, tensor V3 perp, tensor W1, tensor W2 perp, tensor U3. And I leave it to you, this is what I will not present today, is really this is the only choice possible because the combinatorics, in order to have a Z3 invariant expression and one that's not identically 0, the combinatorics essentially force this on you. But now there's a slight subtlety in that here I have points in projective space, here I have vectors, and I may have made a bad choice of scale, so let me divide by some things. So let's see, lambda will be U1 perp evaluated on V2, V2 perp evaluated on W1, and W3 perp evaluated on U2, because I made a, this is what we need to fix the scale, and mu is similar. Did I make a mistake here? This is probably a 2. No, 3. Like that. Now, I'm not going to prove this theorem for you today, but there's a mindless proof that you could do. Namely, just pick these 3 points, plug in, and check that you have matrix multiplication. But I can also suggest a more geometric proof without making any choices. Namely, we know that this matrix multiplication tensor is the unique tensor invariant under the group SLU cross SLV cross SLW. So all we need to check is that this tensor is invariant under this group. But this construction is Z3 invariant, so we only need to check that the tensor is invariant under this group, and these two will follow automatically. And then to check that it's invariant under this group, you can in fact just check that it's invariant under its Lie algebra action, and that is a very straightforward calculation, purely geometrical without any choices. Questions?
So, what about the dimension counts is the usual expected dimension of the fiber is dimension 5, right?
Fiber of what?
So in your diagram, so
Over of this S,
yeah.
S 7 0 over sigma 7 0. Yeah, except that matrix multiplication is not a general point in this variety. It's a very special point. And therefore, its fiber is larger than the fiber over a generic point. That's a good remark. And I had mentioned that yesterday, the fact that this fiber is large almost makes matrix multiplication true. If the fiber were any larger than it is, matrix multiplication would somehow be trivial tensor modulo topology. And in fact, what I want to argue, and I might as well say it now, is that because this fiber is so large, it's completely reasonable to expect that the border rank of matrix multiplication should be strictly less than its rank. That is, we have, if matrix multiplication lies on some Rth secant variety, it will almost certainly lie on the boundary of that variety, not in the interior, because of its extra symmetry. And in fact, more generally, any tensor with a large symmetry group, we would expect its border rank to be larger than its rank. That is, we would expect it to be on the boundary of this variety. Other questions?
Is it also true that these are all the possible expressions?
Yes, so that follows by a theorem of de Groot. Yes, so we did not prove that, but it is true because of an earlier theorem
So in this
by
case,
de
we
Groot.
don't have to consider the orbit closure, just one orbit.
No, because now we have to decide what we mean by by expression. Rank 7 expressions. If I said border rank expressions, then we would have to consider the closure. And there are things in the closure that are not of this form. You can just take limits. But as stated, these are the only rank 7 expressions, but there are border rank expressions that are different from these. Good question. Other questions? Okay. So now we go to our second topic of border rank algorithms. And I'll need to just talk a little bit of preliminary about border rank algorithms before returning to the special case of matrix multiplication. So we have some projective variety. We have some point that's on the Rth secant variety, but is not on an honest R secant plane. then there exists a curve in the Grassmannian of R planes in V, continuous, such that for all t greater than 0, E of t is spanned by, say, x1 of t up to xr of t and xj of t are in x, and 2, that our point is in E0, this limit as t goes to 0 of Et, and this limit exists because the Grassmannian is compact. Now, these points in projective space is also compact. And so, in particular, x1 of 0 up to xr of 0 are linearly dependent. Otherwise, E0 would be a rank expression. So, how can R points on an algebraic variety fail to be linearly independent? Well, how can this happen? Well, the first case is kind of the trivial case. 2 points coincide. So we have x1 of t, and here we have x2 of t, and they both coincide at 0. Let's just look at that. So we have this, in the Grassmannian, we have this x1 of t wedge x2 of t. And let me write this out in Taylor series. Let's write this as x1 plus t x1 prime plus order of t squared, wedge x1 plus t x2 prime plus order of t. So this is a prime plus order of t squared, like that. So I can rewrite this as x1 wedge x2 prime minus x1 prime plus order of t squared plus, like that. Order of t, I can divide by t since I'm in projective space, Grassmannian. So in this case, can get any point on the span of the tangent space to x1 at x, on the tangent space to x1 of x. And if we had a third point coming in, well, let's not do that. Now, let's say we had 3 points. 3 points fail to be linearly independent. That is, 3 points lie on a line. So here we have some line. Here we have x1 of t coming in. Here we have x2 of t coming in. And here we have x3 of t coming in. And in the limit, so this is like x1, this will be x2, and this will be, say, x1 plus x2 after rescaling. And I claim in the limit, so I'll leave this as an exercise, could get any point on the span of the tangent space to x1 of x, the tangent space to x2 of x, and the tangent space to x3 of x. Now, you may be concerned here because this looks like 3 tangent spaces, and we should only, by dimension count, we're on the third secant variety. It looks like we're violating a condition. But there's actually a relation between these 3 tangent spaces. And in fact, this third tangent space is not needed. And more generally, any r plus k, not say r, let's say k points limit to be on a p k minus 2 contained in x. Now, if x is an arbitrary variety, it may not contain large linear spaces, so that option may not occur. But in our case, I will describe, so for most x, do not have large linear spaces. But for the Segre, we do. So we can take sub p a prime cross some b cross some c. This is a linear space. And similarly with the other factors. So the Segre has lots of large linear spaces on it. Now, there's more interesting situations. So for example, if x is the Segre, we have V3 of P1, the twisted cubic sits inside P3, but we could also think of this sitting inside the Segre of P1 cross P1 cross P1, which we can sit inside our larger Segre. So if we take 5 points on a twisted cubic, we get a more exotic limit. Now, I do not know whether it is a consequence of the people who write algorithms for matrix multiplication or for some other reason, but in all the algorithms I have seen in the literature for border rank expressions of matrix multiplication, all the limits have used linear spaces, have just used linear spaces. Now, I do not know whether that is an artifact of the methods that people who write algorithms use, or whether there's something special about linear spaces and the twisted cubic is not. I mean, for us as algebraic geometers, we like interesting curves on algebraic varieties that lie on linear spaces. But the computer scientists have not discovered this. I do not know why. So let me try and we do not have very much time, but oh, we still have some time. Good. So let me remind you at least what the lines on the Segre are very explicitly. So let's restrict to the case X is the Segre. And our point is this matrix multiplication. I'm not going to restrict to square multiplication, arbitrary matrix multiplication. And in fact, today, since we only have a small amount of time, I'm going to focus on M2 to N. So this is inside C2N tensor C4 tensor C2N. So part of the problem is we don't know usually where to look. We don't know what's the correct value of R. So it's classical. Well, first of all, Strawson's equations imply that the border rank of M2 to N is at least 3/2 times 2n, which is to say 3n. It's classical, that is, just by flattenings, you could see that the border rank of M2 to 1 is equal to 4, which is 3 times 1 plus 1. I showed that the border rank of 2 by 2 matrix multiplication is 7, which is 3 times 2 plus 1. Bini, Capovani, Lotti, Romani show that the border rank of M2 to 3 is at most 10, which is 3 times 3 plus 1. And let me give you their proof. So the proof, recall that this TBCLR is a map like this. And M2 to 3 is a map like this. And let me just use some color to give you the proof. Namely, we can write this matrix multiplication tensor as the sum of two of these. And we saw that the border rank of this is 5. Then there's been some recent work by Smirnov and collaborators some papers by him, some papers by other people, where they showed R of M2 to 4 is at most 3 times 4 plus 1. R of M2 to 5 is at most 3 times 5 plus 1. R of M2 to 6 is at most 3 times 6 plus 1. R of 2 to 7 is at most 3 times 7 plus 1. And in general, R of M2 to n, they couldn't prove that bound in general, but it's less than 3n plus 2 is what they could prove. So we have a lower bound of 3n, an upper bound of 3n plus 2, and some evidence that 3n plus 1 might not be unreasonable. So, open question. Which of these three numbers in general? So for small n, it's 3n plus 1. But already for 3, we don't know. This is only an upper bound. And if you look, this one, Strawson tells us that the border rank is 5. But there's no reason that the best algorithm for this is obtained by splitting it into two tensors. The best algorithm may be more exotic. So that's an open question. So what I'd like to describe today is a project with Nick Ryder, a graduate student at UC Berkeley. Is analyze the geometry of this tensor and Smirnov's. So I will only do one example because we have very limited time, and if you want, I can talk in private explaining you some of the other ones. It's also very much work in progress, so I will have to, the ground may shift a little before the article is written. So let me review. As I said, all the algorithms that I've seen in the literature come from linear spaces. So let's study lines on the Segre. Well, there are three types. Let's call them alpha lines, where I take a P1 inside PA and consider P1 cross some B cross some C, where this is in PB, this is a point in PC. And then there are corresponding beta lines and gamma lines. The beta line, I choose a line here. The gamma line, I choose the line here. So these lines, these three types of lines, they're parametrized by Grassmannian of two planes in A, and PB and PC for the alpha lines, and similarly for the beta and gamma lines. So those are our three types of lines. Now, in our case, there's even more structure. This is the macroscopic, the external structure. We also have internal structure because, for example, PB is P of V star tensor W, space of matrices. And inside here, we have the Segre, P of V star cross PW. And so inside here, not all P1s are created equally. There are special ones that respect this additional structure. So let me call these nu star lines and omega lines. So a nu star line, I take a line in V star and a point in W. And an omega line, I take a line in W and a point in V star. Now notice that the omega lines, there's only one. They're all of the form, since W is C2 in the way I've chosen it, that omega lines are just all of the form nu tensor nu cross PW, because PW is a P1. So the omega lines are limited in how they're parametrized. They just involve a choice of a point in this space, and I get an omega line. Now, I just did not want to erase that, but I didn't. So here's my A, well, here's my B, here's my C. My choice here destroys the Segre structure in this space pretty much. But not in this space and not in this space. So in PC, I have EW star tensor U. I have omega star lines and mu lines. And again, these omega star lines, these are correspond to points in PU. But now, this choice of this x22 being zeroed out, we have distinguished a basis in some sense. So this choice essentially, up to scale, fixes bases of U and V, and also the dual vector spaces. Now, our expectation since we only have this SLW freedom is we would either, and now this is going to give the opposite answer to your question this time. So either a family of expressions, and by expressions I mean curves in a Grossmanian, parametrized by SLW, or a single SLW invariant expression. Now, let me remind you of one more thing. If I have a point of the Segre, then the affine tangent space of this point, well, if I have a curve in this Segre, what does that mean? It means I have a curve in my first vector space, a curve in my second vector space, and a curve in my third vector space. And when I take the derivatives by Leibniz rule, I can have anything derivative here, and these two stay constant, plus this one constant and this one constant, any derivative here. So the upshot is my naive tangent space is A tensor, at this point, is A tensor B tensor C plus little a tensor B tensor C plus A tensor B tensor the vector space C. Is this okay, or should I prove this? It's okay. Right. Now, what I alluded to before, if I have a line in the Segre that is a P1, say L is the span of, say, some A1 tensor B tensor C and some A2 tensor B tensor C. then the tangent space to any point on this line of the segre is actually contained in the tangent space of any other 2 points. And like I said, this is actually a special case of a very general fact about lines on projective varieties. So because of that remark, it makes sense to write tangent space to L of the segre. So this is the span of the tangent space to the segre of any 2 points on L. Why do I want to introduce this language? It's because I want to describe things as geometrically as possible. So I want to make as few choices as possible. So here's, I don't know whether it's a theorem or a proposition. So let's let L1 be x21 tensor v1 tensor w tensor z11, L2 equal x12 tensor y12 tensor w star tensor u1. So this is an omega beta line, and this is a omega star gamma line. And those 2 lines are in skew position. Span of L1 and L2 is a P3. Like most, anytime you take 2 lines, if they don't line a plane, they'll span a P3. So, if have 5 points in the span, can get an arbitrary linear combination with 2 on L1, 2 on L2, and I don't care where I put the 5th point. We could get an arbitrary linear combination of tangent vectors. Well, can get, let me say it this way, any vector in the span of TL1 of the segre and TL2 of the segre.
This TL segre is the same as the union of the whole tangent space.
Right.
Yeah.
But it's also the same as the span of any 2. And that's important because I only am allowed 5 points. So I need 2 on my first line and 2 on my second line. So I'm allowed to have that. So everything works out just right. And the content of the theorem, as you've already guessed by now, is that this tensor, listen here. So this gives a purely geometric description of the Bini-Capovani-Lotti-Romani algorithm which was initially found by accident and with a computer. And notice there's really it looks like there's coordinates here, but there isn't. These points are uniquely determined by my choice of x22. This is sort of the two things that are on lines that are connected to x22. And then these are the annihilators. This is, well, let me not go into detail. But there's really no choices involved here other than the choice of x22. And maybe one last remark. I have these two skew lines, but there's also, it plays no role in the algorithm, but it is interesting from a geometric point of view. There's a unique alpha line that crosses the two of them. So we have a beta line and a gamma line, and then there's a unique alpha line that intersects them. I don't know if that has any important role to play in future work. Thank you for your attention.